Hello everyone, welcome back to Algebra 1 with Miss Betsy. Today we're going to be talking about square roots and radicals. If you'd like to follow along with me in your text, we're going to be on page 69, which is section 2.6 in our text, Algebra 1 for Christian Schools, published by Bob Jones University Press. You need to remember and realize that second edition and third edition are not compatible directly with page numbers and chapter numbers, but you can still learn the same material regardless of what text you're using, even if it's not a Bob Jones University Press publication. So let's go ahead and pray, and then we'll see what my lame joke is for the day and get started. Father, I thank you that you love us, and I thank you that you are always present with us. I ask that you would help us today to learn this new material from our algebra text, that you would help us to be diligent in all that we do, and that you would help me to communicate clearly to those who might be watching this video. Thank you that you love us, and I pray in the name of your Son, Jesus. Amen. Okay, the joke for today, it's recycled from last year, but it's still a pretty good one because I know I've got some new people out there. What do you get when you cross a dinosaur and a case of fireworks? Well, you get dynamite. So, let's say that we have something that's become very popular in lots of areas of the country. It's square foot gardening, and it's where you take a small amount of space and still are able to produce a nice sized harvest if you're just interested in having a little bit of food extra on your dining room table, on your dinner table. So let's say that you have a 16 square foot garden, or a garden that encompasses 16 square feet. And you want to find out the dimensions of that garden. So what you're looking for is actually two equal factors whose product is 16. And why do these factors have to be equal? Well, it's because with a square, all four of these sides are going to be the same. So I should put 16 square feet. Square feet, of course, you'll remember talking about area. And how do you find area? You find area in general by taking length times width. Except within a square, those sides are the same. So as I said, we're looking for two equal factors, that when you multiply them together, you end up with 16, and they have to be equal because we have a garden. I'm sorry, not because we have a garden. They have to be equal because it's a square. So all four of these dimensions are going to be the same. And the process that we are going to use is called finding the square root. So what is a square root? A square root is one of a number's two equal factors. One of a number's two equal factors. And we've got a little bit of math vocabulary going on here. You have to know that the things that you multiply together are called factors. Factor times factor equals product. So if we had 2 times 5 equal to 10, then what would our factors here be? 2 is a factor, 5 is a factor, and our product is 10. What we're looking for now is two factors that when you multiply them together, you end up with 16. But not only two factors that multiply together that equal 16, they have to be the same factor because we have a square going on. So let's just think in general, how do you come up with what two factors would equal 16? Well, obviously, 1 times 16 is 16. 2 times 8 is 16. But these factors right here don't meet our solution because we have a square garden here, so the factors have to be the same. And obviously, the number that we're looking for is 4 times 4 is equal to 16. So if you understand, right here with our garden, we have 16 square feet. And the way we got that 16 is to multiply 2 of those sides together. This is 4 feet, and this is 4 feet. You can go backwards into that problem. And this whole idea that we've illustrated right here is what's going on when we take the square root of a number. Square root is one of the number's 2 equal factors. We have 2 factors here, don't we? You might think at first that it's only 1 factor because it's a 4, but we have to say this 4 times this 4. When we multiply those 2 factors together, that is how we arrived at the 16. And that's why we say that a square root of a number, that the square root is one of a numbers. And what number are we using here? We're using 16. It's one of the number's 2 equal factors. There's 4 times 4. 1 times 16, those are factors of 16, but they're not equal. 2 times 8 is equal to 16, but they're not equal. So the square root of 16 is 4. Now, let's look at this. The symbols that we're going to use when we find square root. That symbol right there is what we call the radical. This is a radical sign, and this right here is what we're going to call our square root symbol. And the number that we are finding the square root of, that's called the radicand. The symbol itself is the radical sign. Okay, so more vocabulary. I hope that this is going to be a review for you. This is the radical sign, this is the radicand, and this means we would read this as the square root of 16. So when I say the square root of 16, I'm looking for one of a number's 2 equal factors. So 4 times 4 is 16. So this would be read, the square root of 16 is equal to 4. And I want to go ahead and show you some examples of what we're talking about. We're going to more illustrate here what's going on. Example number 1 says, find the square root of 25. And this is on page 70. What is the square root of 25? Well, we are looking for one of the number's 2 equal factors. And how can you express 25 if you were to prime factor that? I don't know of any other way to come up with a product of 25 than to say 1 times 25 or 5 times 5, which is the same as saying 5 squared, isn't it? Because this expression here means that we are going to use that 5 as a factor twice. So if the square root of a number is one of that number's 2 equal factors, we have 2 factors of 5 here, then the square root of 25 has to be equal to 5. Another way that we could have written this, we could have said that the square root of 25 is the square root of 5 times 5. There, it's just screaming obvious at you, maybe even more so than over here with the radical notation, with the exponential notation rather, that we have 2 factors of 5. The square root of a number is simply one of those equal factors. Notice that there's not a radical sign involved here. It's just 5. Okay? Now, example number 2 tells us to evaluate the square root of 36. Evaluate the square root of 36. We're looking for one of that number's 2 equal factors. And there are a number of ways that you could factor 36, aren't there? You could say 1 times 36, 2 times 18, 3 times 12, 4 times 9, or you could say that the square root of 36 was 6 times 6, 2 factors that when you multiply them together, you get 36. Here, 36 is called what? 36 is called the radicand. This long check mark is called the radical sign. The square root of 36 is one of the 2 equal factors of 36. So the square root of 36 is simply 6. Now, we're on page 70 now, and let's talk a little bit differently here. We're going to expand the idea of square roots just a bit. If I take 3 and I use it as a factor twice, I can show that with exponential notation just right here as 3 squared, right? Well, what is 3 times 3? 3 times 3 is 9. But what happens now if I were to say negative 3 times negative 3? How would I use that with exponential notation? That would be the quantity negative 3 squared. What do you get when you get the product of 2 negative numbers? A negative 3 times a negative 3, both of those signs are negative, so we end up again with a product of 9. And you see that we have 2 different numbers that can be used as a factor twice that results in a product of 9. And you have that for every example out there. We just did 36 and we said, well, it's not 1 times 8, 36, 2 times 18, 3 times 12, 4 times 9, but it's 6 times 6. So we said that the square root of 6 times 6 was 6, but you could also have done that as negative 6 times a negative 6, which would make you think that the square root of negative 6 of 36 could also be negative 6. And this is where we get into a shade of definition and what we're going to use all of the time, or at least for now. We're going to use what they call the principal square root. So principal square root. That's always the positive factor, or the positive root. There's also this negative 6 here that is a root. It's a square root of 36, but we're always going to be looking for the positive factor, or for the principal square root, unless they ask you to find, and I think they're going to call it the negative square root. Yeah, unless you're asked to find the negative root. So we have the principal square root, and we have the negative root. We're going to automatically default to the positive number that is used as a factor twice. So let's look at 4. What number do you use as a factor twice? Well, you can say 2 times 2 is 4. You can also say negative 2 times a negative 2 is 4. But if they ask you to find the square root of 4, that's always going to be equal to 2, because we're going to use our positive factor, which is called the principal square root. And I know you're thinking, good grief, Miss Betsy, you've told us this a lot. Well, I'm saying this to help cement in your mind this vocabulary here and give you a chance to take a note or two. We're going to use the principal square root, which is the positive factor of that number. Let's see, there are some radicals that do not have rational numbers as square roots, and they're called irrational numbers. This is more vocabulary here. A rational number is something that you can write in a form that it looks like a fraction to you. 2/3 is obviously a rational number because it looks like a fraction. But 3 is also a rational number because if you divide it by 1, it looks like a fraction, but it still has the same value, 3. Similarly, we think of 0.1 or 0.1 as a decimal number, but what is that actually? It's 1/10. So you can also express that as a rational number where we have a numerator divided by a denominator. So the 0.1 is also written as 1/10. If you have the square root of 4, that's written as 2, because 2 times 2 is 4. If we wanted to write that as a rational number, or show it technically as that rational number, that fraction, we would write it 2 divided by 1. But there are far more square roots that you can't write as a fraction. Square root of 5 is one of those. There's not an integer that if you use it as a factor twice, here, the square root of 4 is 2. 2 is an integer. When you use it as a factor twice and you say 2 times 2, you get your radicand back, correct? 2 times 2 is 4. What number is there that when you multiply it together, multiply it twice, you get 5? This is a very common mistake that kids make. The square root of 5 is not 2.5 because it's true that 2.5 plus 2.5 is 5. 2.5 times 2.5 does not equal 5. 2 times 2 is 4. 3 times 3 is 9. But there are no integers that when you multiply them together will give you a 5. 2 times 2 is 4. 3 times 3 is 9. 5 falls somewhere in here. What did we say this radical is? This represents an irrational number. More review of vocab that you need to know. Irrational numbers cannot be written in the form of numerator over denominator. Okay, we talked about how we have the principal square root of a number. We have the negative root of a number. But what if we have, this is example number 4, something that looks like this? We want to find negative sign, radical sign, 16. What are we looking for here and how do we read it? This is something that we would read here instead of minus the square root of 16. This says the opposite of the square root of 16. So first you calculate what the square root of 16 is, and that's going to be 4. So this is the opposite of, we can do the square root of 4 times 4. So negative 4 is the solution to this problem here where we have the opposite of the square root of 16. This right here is not the negative root. Because we didn't use the -4 times -4, we had the opposite of the square root of 16. Okay, let's see what I want to do next. Be careful that you do not confuse taking the square root of a number with squaring a number. This is right here on the bottom of page 70. Don't confuse taking the square root of a number with squaring a number. Finding the square root is the inverse of squaring. This is the square root of a number. Square root of 4 is equal to 2. Let's take this number 2 and square it. 2 squared is equal to 4. These are inverses because we started with 4. First we started with 4. Then we took the square root of 4, which was equal to 2, right? Then we took that 2 and we squared it again. And what was the result of that? 4. We started with 4 and we ended with 4. So square roots and squaring are inverses. And squaring a number. These are inverses just like addition and subtraction are inverses, and multiplication and division are inverses. If you take a number, you find its square root. To undo that, you square it again, you square your result, and you began with a 4 and you ended with a 4. On page 71, it talks about how the radical sign is used to talk about other roots besides just the square root. So let's look at that and see how we're going to pronounce these. That's the square root. If we have a 3 right there, that's what we call the cube root. If we have roots, okay? My hand and mouth can't keep up. Cube root. If we have a 4, that becomes the 4th root. If we have a 5, that becomes a 10th root, right? No, you see the pattern. If you have a 5, it's the 5th root. And now is when it just sounds really weird math speak, and it is, but I think you see the pattern. Cube root, or you could also say 3rd root, 4th root, 5th root, 6th root, nth root. And that's just a weird sounding thing in English to us because we may not be used to thinking mathematically. But all this is saying is whatever this number is here, that's what root it is. If this is a 10, it's the 10th root. If this is a 7, it's the 7th root. If it's 100, it's the 100th root. And there's no application that I'm aware of where you're looking for a 100th root. But that would still be what it is called. We've got this small number here that's to the left, upper left part of the radical sign. What is this going to be called? This is called the index. You have to know your vocabulary. You have the index, you have the radical sign, and what is underneath here? This is called the radicand. Radicand, root, and index. I'm sorry. Radicand, square root symbol, and the index. The index tells us which root we're going to be taking. You notice we don't have a 2 up here. If there's not an index showing, we assume that they're talking about the square root. So I'm sorry that there's so much vocabulary here, but this is vocabulary that without an understanding of it, you can't do your problems. Once you understand your definitions, then the problems are very, very straightforward and very simple. So if a square root is one of the numbers 2 equal factors, what would a cube root be? A cube root is going to be one of a number's 3 equal factors. So if we want the cube root of 8, well, it just so happens that 8, when you prime factor it, is 2 times 2 times 2. So 8, when you have 3 factors together, they're the same. 2 times 2 times 2. The cube root of 8 is one of that number's 3 equal factors. Cube root of 8 is 2. Similarly with the 4th root. If we wanted to take the 4th root of 16, that root is going to be one of that number's 4 equal factors. 2 to the 4th is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. So the 4th root of 16 is 2. Remember, we're not writing the radical sign here. We're not using the index. We're just showing one of whatever that factor is that is used multiple times. Let's see. We want to do example 5, 6, 7, 8, 9 on page 71. And they're not going to be reviewing a big way of factoring these numbers yet. They're just sort of reminding you of the general idea of finding roots that we learned in pre-algebra. Example 5 says find the cube root of 27. So we're looking for a factor of 27 that if you use it 3 times, you're going to get 27. They're going to have you at some point remind you that you're going to prime factor. So we'll just go ahead and start it now. If we take the prime factorization of 27, 3 times 3 times 3, that becomes the cube root of, instead of saying 3 times 3 times 3, I'm going to say it's the cube root of 3 cubed, because this simply means that 3 is used as a factor 3 times. Now I want you to particularly observe that the index on the outside and the power on the inside are the same. Index and power are the same. We're looking for one of that number's 3 equal factors, which is 3. The cube root of 27 is 3. Next problem we have is simplify the cube root of -8. Typically, well, at least for a while, when you are solving these problems, there's not going to be a radical symbol in there anyway, because we're only going to deal with what they call perfect squares, perfect cubes. So if we want to find the cube root of -8, you remember that if you have an odd number of negative factors, you have a negative product. -2 times -2 is 4. -2 times -2 times -2. So positive 4 times the -2 is -8. If you have 4 factors of -2, you have a positive 16. And if you have 5 factors of -2, then you have a negative 32. We saw that there was a pattern that as long as you had an odd number of negative factors, you had a negative product. Here we see that if negative 2 is used as a factor 3 times, negative 2 used as a factor 3 times, negative 2 times negative 2 is 4, times negative 2 is negative 8. So our cube root of quantity negative 2 cubed is the negative 2. And you notice that the index and the power here are the same. We want to find the fourth root of 625. This is example 7. The fourth root of 625. Okay, some of these numbers are going to look to be really big, but they're just repeated multiplication of a fairly small number. For example, you know that 5 squared is 25. And you may have learned by now that if you have 5 cubed, or 5 used as a factor 3 times, that's 125. We want to find a fourth root, so we're looking for a number that's going to be used as a factor 4 times. Real good possibility that 5 to the 4th is going to be 625, don't you think? Well, it is in fact, and you can verify that. 125 times 5, 2, is in fact 625. So if we prime factor 625, let me just go ahead and do that. 625 and say, I don't know how to factor that. Well, you know that you can divide it by 5 because it ends in a 5. So 5 goes into 625 125 times. You can divide by 5 again, get 25, divide by 5, and all of these factors that are on the outside of that ladder are 5s. So we have 5 used as a factor 4 times. So it's the fourth root of 5 to the 4th. You see that the index and the power are the same. So the fourth root of 625 is 5. Now let's look for the fifth. Okay, example 8 says find the fifth root of 1024. Just play around with these. Don't let them suck you into thinking you've got a hard problem going on here. 1024. And we want to have the fifth root of that. Now we already know that it can't be 5, right? How do we know that? It can't be 5 because the number here, 1024, doesn't add in 5. So you could have 2, 3, or 4. Let's just think, we're looking for a fifth root. Well, we just said that 2 to the 4th was equal to 16, didn't we? If I can write this, 2 used as a factor 4 times is 16, and then we multiplied it by 2 again. 16 times 2 was 32. To get the fifth root of 32 is 2. So clearly, it can't be 2 used as a factor 5 times. Can't be 5 used as a factor 5 times. What about 3? Well, you learned, you probably know this one, and we just did it in class, that 3 cubed is 27. Well, what's 27 times 3? That's 81. What's 81 times 3? Nowhere close to 1024, so it can't be 3 either. It's making me think that we must have 4 is the number that we're looking for. What is 4 squared? 4 squared is 16. So let's just see what happens 4 times 4 times 4 times 4 times 4. If we use 4 as a factor 4 times, 5 times, I'm sorry. 16 times 4 times 4 times 4. 16 times 4, 64 times 4 times 4. What is 64 times 4? That's 256 times 4. Now let's go ahead and multiply 256 by 4. 4 sixes are 24, carry 2, 20, and look at that. If we use 4 as a factor 5 times, we end up with our radicand, which is 1024. So the fifth root of 4 to the fifth is 4. You think, wow, how can it possibly be a 4? It's because we have this repeated multiplication going on. 4 times 4 is 16, times 4 is 64, times 4 again is 256, times 4 one last time gives us 1024. Now, let's look at example 9. I'm sorry this is a long video, but it is what it is. We want to find the opposite of the square root of 9/4. There's an additional property that we're going to learn just down the road of a different way to find the square roots of fractions or the square roots of rational numbers, but I'm deliberately not going to show you now. If, however, you know how to do that, you know what I'm talking about, and you want to use it, that's just perfectly fine. Let's say that 4 ninths right here is our product, isn't it? Because if we want to find the square root of 4 ninths, what we're looking for is one of the numbers 2 equal factors. So we're going to have 2 fractions that when we multiply them together, we have to end up with 4 ninths. And you remember that when you multiply fractions, you multiply numerators, you multiply denominators. What times what gives us 9? Is 3. What times what gives us 4? Is 2. So we can write 2/3 as a factor twice. The opposite of the square root of 2/3 times 2/3. What is the square root? It is simply one of a number's 2 equal factors. We don't use the radical sign, so we have -2/3. Is the square root the opposite of the square root of 4 ninths? That answer is -2/3. You could also have written that, looking at it a different way, is we have 2/3 used as a factor twice. And remember, I've been illustrating that if the index and the power are the same, your solution is just this number in here. Well, the index and the power are the same, so we have the opposite, or we have -2/3. And you say, oh, Miss Betsy, there's not a 2 out there. You're right, it doesn't show up, but remember we said if there's not an index indicated, we're talking about the square root. So we have the square root and the power are the same. Square root of, the opposite of the square root of 4 ninths is a -2/3. I promise you, the more you work with these, the more comfortable you'll get with them. At some point, it may just be frustrating to you where you want to tear your hair out or throw your pen across the room. Don't do that. You know, just get up and go take a break for a moment, get a bite to eat, go out and ride your bicycle, text your friend, but take a break and come back and work on your math again. Now we want to find out, if I can make my bifocals work here, we want to find out the cube root of a -27/125. Let me cap up one of these pens. the cube root of negative 27 over 125. You're looking for one of the number's 3 equal factors. This is where as you use these, you'll say, oh, I remember how I get 27. If I say 3 times 3 times 3, that gives me 27. 3 times 3 is 9, times 3 is 27. So you can also express that as a 3 cubed, couldn't you? And what if you use as a factor 3 times gives you 125? Well, 5 times 5 times 5 is 125, which is 5 cubed, isn't it? We're looking for factors here that when you have the same factor multiplied 3 times, you end up with this fraction here, the negative 27 over 125. So what they're asking us to do is realize that this is a negative 3/5 that we are using as a factor 3 times. Because 3 times 3 times 3, 27. 5 times 5 times 5 is 125. And we have an odd number of negative factors. I'm sorry, I know I'm speaking Greek to you. We have an odd number of negative factors, so our product is going to be negative. What do I mean by that? Let's look at this. Negative 3/5 times a negative 3/5 times a negative 3/5. That's what this expression here means. When you multiply a negative times a negative, you have a positive, don't you? 3 times 3 is 9. 5 times 5 is 25. So now you have 9/25 times a negative 3/5. We have a positive factor. We have a negative factor. When you multiply a positive and negative together, you always get a negative result. 9 times 3 is 27 because we multiply numerators. 25 times 5 is 125 because you multiply denominators. And you see that we have negative 27 over 125. So the cube root of this negative fraction here is simply negative 3/5. All of the parentheses go away, the radical signs go away, the index and the root, because what this is asking for is one of those factors that is used 3 times. One of those factors. So that's what our solution is here. Now, example 11 and example 12, I think the terminology here is a little bit confusing. This is not a hill to die on. And let me show you a different way to consider what they're asking you for. Example 11 says, write square root of 25 is equal to 5 using exponents. And frankly, that's confusing to me. Maybe that makes perfect sense to you, but it doesn't speak to my mind in a way that makes any sense at all to me. So let me write your instructions differently. Remember when we're talking with commutative property, associative property, and the distributive property, we said write an equivalent expression for 3 times 9 using the commutative property. How can you write it differently? Well, you said that 3, apparently I left the marker off her, that 3 times 9, you could also write that as 9 times 3. They both mean the same thing, don't they? Well, see if you can write something that means the same thing as the square root of 25 is equal to 5, simply by using exponents. Well, is it true that 5 squared is equal to 25. We're saying the same thing. This says that one of the numbers' two equal factors is 5. Or one of the square root of 25 is talking about one of the factors of 25. Here we say use 5 as a factor twice, or square it, and we come up with 25. Try and make some sense out of this. I have no better way to communicate it to you, and I apologize. The next one says, write 4 cubed equals 64 using radicals. Write 4 cubed is equal to 64 using radicals. What I'm saying is write an equivalent expression. How can we say something that means the same thing? What this means is that if you use 4 as a factor 3 times, you get 64. But if we want to say, okay, a radical, I have to use a radical symbol. Well, if I say the cube root of 64, this is asking for which one of those factors, what factor is it that you can use 3 times to come up with 64, and that's 4. This here says use 4 as a factor 3 times to get 64. This here says tell me what that factor is that you're going to use 3 times. Study these, see if you can make sense out of them. I hope it's just simple to you and that this is something that I just have a brain freeze over. But you're going to find those sample type problems on 21, 22, 23, and 24 in your homework. Now, something else that we need to recognize, and this right here is really easy compared to some of the stuff we've been doing. I've been thinking, we've talked about parentheses, brackets, and braces as being grouping symbols. We have some more grouping symbols, and that includes the radical sign, it includes our fraction bar, and includes absolute value bars. Example 13 says simplify this expression here. 8 times the square root of 5 plus 4. That radical symbol there, in this case it's specifically the square root sign, that's a grouping symbol, and it says do me first. We have to add inside there, and we now have 8 times the square root of 9. And we just finished reminding ourselves of what it is to take the square root of a number like this. And we're looking for one of that number's 2 equal factors. You can rewrite that as 8 times the square root of 3 squared. 8 times 3, 24. All we did here was use this radical symbol as a grouping indication to say first we've got to add 5 and 4 together, because then we end up with 9, and we know that 3 times 3 is equal to 9. Alright, our next thing says, example 14, 7 plus 11 over 3. This, I'm really not even sure why they have the example here. 7 plus 11 over 3. You guys already know that with this you're going to add the numbers in the numerator together first. To get 7 plus 11 is 18 divided by 3, and 18 divided by 3 is 6. That division bar or that fraction bar there is simply used as a grouping symbol. And the final example that they have here is using absolute value bars as grouping symbols. We have 2 times the absolute value of 5 minus 14. Absolute value bars are grouping symbols. Work inside of those first. What is 5 minus 14? 5 minus 14 is a negative 9. What's the absolute value of a negative number? It's always its positive counterpart. 2 times 9 18 is the solution that we're looking for, or the correct value of this expression. Now, those are all of the examples that we're going to talk about here, but we're reminded again at the bottom of this book what I've said repeatedly in class, in pre-algebra and algebra 1. Anything that I teach is to remind you that there's great value in memorizing the squares of numbers. From 1 to 20 they suggest here. I say at least 1 to 15 because it will make it very much easier for you when you are finding square roots. 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 times 7 is 49, 8 times 8 is 64, 9 squared is 81, 10 squared is 100. Let's do some more. 11 times 11 is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, 20 squared is 400, 25 squared is 625. Go ahead and take the time to learn 16 squared, 17, 18, 19 squared, because 2 squared is 4, and the square root of 4 is 2. If we want to take the square root of 4, it's going to be one of that number's 2 equal factors. The square root of 9 is one of that number's 2 equal factors. Square root of 16 is one of that number's 2 equal factors. One of that number's 2 equal factors. You see the pattern that we have going on here? And why it's going to be very much to your benefit to have these memorized. And what I'm writing here shows you how it's a good example for you, or a good illustration for you, of how squaring a number and then taking the square root of it, how those are inverse operations. We started over here with 9, we squared it to get 81. Then we took the square root of 81 to get to the 9 that we began with. So what would the square root of 121 be? It's going to be 11. The square root of 144 is 12. The square root of 169 is 13. The square root of 225 is 15. I know that you see what I'm illustrating here. Trust me on this. Memorize your squares. At a minimum, up to 15 squared, then also 20 squared and 25 squared. It'll make your job a lot easier, and it'll be less frustrating to you and less time consuming. That is finally the end of section 2. Whatever we're in, section 2.6, square roots and radicals. Send me a text, ask me a question in class, and I'll see you next time.